Sorry, I have to do that. I don't know. It's my dad. My dad taught me that. All right. So I am now recording. All right. And so what you see up here is what will be on the video that you'll be able to get to later, and you'll be able to hear me. All right. I did set up the Canvas page, so I wanted to show you. If you log into your ACES account, and you click on your courses, you should be able to find your pre-calc class there, along with your other classes. And this is what I set up yesterday, I think. It's very primitive. There's not a whole lot here. Your syllabus, your schedule. Did I put a schedule there? Where does that go? I didn't think I put a schedule. Maybe I did. Oh, I did. I forgot I did that. Did you have a copy of this? Okay. So there it is. I didn't bother to change it because I don't know how things are going to work out here, when what we're going to wind up pushing or squeezing, or so I just figured as we go, this will somehow change, and I'll either tell you what the changes are, or I'll make the changes here, and then I'll just tell you, hey, go look back on Canvas. I updated your schedule. The syllabus is there, and then I told you that everything I write down here will be saved to a file that you'll be able to go find later and print. If you click on Files, I have a folder here for you now that says Class Lecture Notes, and then there's your calendar. The only thing I don't have is, I guess there was a formula sheet that you were allowed to have on that first test. Is that correct? Was that handed out to you? It was what? Okay. Oh, okay. So it was given to, from where though? On ACES. Okay. Okay. Yeah, I know. So, all right. What I plan on doing is giving you a new one, and since we haven't started really a lot of the trig stuff, I'll give you one that's all trig. It looks like that's the one you just showed me, sir. That was a lot of college algebra stuff on there, right? And conics. Yeah. So I'll give you another one. So I'll post it. What I'll have here is probably another folder that says like review sheets, formula sheets, or something like that. And then as we start moving along and we start to have reviews for the exams, I'll post them in here. So just be aware of where things are. And then finally, on this first page is the videos. So everything that I do, I will post up on YouTube. So when you click here, it'll take you to the channel, the playlist for this class. And right now there's no videos in here, but they'll just start to appear here. And I believe that the newest one will be on top, or it's the other way around. I can't remember how I have it organized. Then you just go back and watch them, all right? You don't have to, but you can. And I can see how many people watch them. So sometimes I get sad when I see that nobody's watched the video. I don't know if that's good or bad. It either means you understood it or no one's watching them. So, all right. So those are the videos. Any questions about the videos? Because I always get people that I actually have students who will sit there, and then like 8 weeks, 10 weeks in the semester, they're like, oh wait, hold on, all that stuff you're doing, that's being recorded? Like I can go watch that? And it's yes, that's what I was saying in the beginning. So is there any question that you will be able to go back and watch these, and this is where to find them? Everyone's good? Okay. Now grades, I'm not going to click on grades because it'll bring up everyone's grades. But if you click there, it should show your grades. I did put all the grades in. And so if you go in there and you notice that there's a discrepancy with something, please just let me know. I think I only had 2 quiz grades and 1 exam grade. That's all I have. People, I think this is just a way that you could get in contact with your classmates if you wanted to. List everyone out in the class. You could email them or something. Just don't harass each other. And I believe that's it. Okay, any questions on this? Some people who are familiar with YouTube sometimes subscribe to my channel. And I don't know, I mean, I don't recommend you do that. Sometimes when you subscribe to someone's channel, then every time they put a video up, you get notified. And I put multiple videos up every single day. So you would probably get annoyed by that at some point. So I don't recommend you subscribe, but you can. All right. Any other questions or any questions? Make sure I've got it all there. Yeah. Okay. Well, at some point we have to start moving forward, so now's the time. I was looking through the notes that it looks like you finished with, and there was some brief introduction of right triangles. So I'm actually going to pick up right there. I'm going to start with the right triangle and just talk about some of the properties of right triangles. So today is really about right triangles. And from the right triangles, we develop 6 functions, 6 brand new functions that we've never, well, you may have seen them, but we'll act like we've never seen them before. 6 brand new functions that we use for the rest of our math lives. All right, they're very important functions. They're the trig functions. So, but they can be established. Those 6 functions can be defined 2 ways. It can be, you can use a right triangle to define them, and then later on we will use what's called the unit circle to define them. And in my experience, like I told you, teaching Cal 1 and 2, the right triangle is important. You definitely need it. But the unit circle, the other approach we're going to take later, is like you have to have that one down. That's the most important one. If anyone walks away from pre-Cal, moving into Cal 1, understanding the unit circle and the trig functions on that is vital. But we have to start somewhere, and I think the right triangle is more natural because we're more familiar with triangles than we are with just an arbitrary circle. Okay, so let's start out. A right triangle, what's a right triangle? Just any triangle? Oh yeah, my notes, the way I'm going to try and do them in here, 7.2 means we're in Chapter 7, Section 2. And then 7.2.1 will mean this is Chapter 7, Section 2, first note. And then I'll go 7.2.2, then 7.2.3. And the reason I do that is if you ever are studying with someone or you're in a group and you're like, oh yeah, call so-and-so, they know what to do. And then you call them, they're like, hey, just look at 7.4.5. That's when he talked about that. You know what I'm saying? It's easier to reference that way, and it's easier for me to guide you later if you need it. All right? So that's the way I'm trying to organize things. 7.2.1, right triangle. So I heard someone say right triangle, what about it? 90-degree angle. So every right triangle, okay, the main property is that it has to have a 90-degree angle. So we draw that little corner, right? Bless you. I'm a little shaky today. Bear with me. So that is a right triangle. Now, just as a reminder, if you have a triangle and we'll have 3 angles in here, right? What do all those angles have to add up to be? Do we know what the sum of the angles of a triangle has to be? 180 degrees. Every right triangle, the sum of the angles is 180. So if this is 90, right, the other 2 together have to also add up to be 90, which means both of them have to be smaller than 90, don't they? So the other 2 angles guaranteed are smaller than 90, and angles that are smaller than 90, we call those what? Acute, right? Acute angles. Obtuse is larger. So we know that the other 2 angles are acute angles. Now for what we're going to do today, we're only going to label one angle, and I'll call it theta. That's a standard symbol for angles, theta. We know right here on the side that theta must be bigger than 0 and less than 90 degrees. And therefore it's an acute angle. We of course know that to be a right triangle, one angle. Is the writing too small? Do I need to go a little bigger? One angle is 90 degrees, right? We know that. Now, the other angle that I'm not talking about here, I could label it if I want to. And I am going to, but we're only really going to deal with one angle today. But I just want to show you some of the notation you might see. We use beta sometimes to represent an angle. So like theta, beta, alpha, Greek letters. Lowercase Greek letters usually represent angles. So just keep that in mind. What else do we want to say here? If I label the sides of this, let's say I label this side A, this side B, and this side C. So what I'm referring to is the lengths of each of these sides. Then the two shorter sides, which would be these two, are called legs. So A and B are called legs. And C is called what? The hypotenuse. Now, there's some other things we can do here when we're labeling this right triangle, using some different language. When you're looking at this triangle and you look across from theta, so here's theta, and I look across to the side that is opposite of theta, we call that the opposite side. Okay, so B is also referred to as the opposite side. But do you understand that B is the opposite side of theta, but B would not be the opposite side of beta, right? What's the opposite side of beta? A. Okay, so whenever you say opposite side, you have to be referring to a certain angle to say that. So if that's the opposite side of theta, then the angle right here, or sorry, the side right there, A, would be referred to as the adjacent, right? That was in your notes, I believe. And then, of course, the C we call the hypotenuse. I'm just going to put hype like that. I believe most of that was in your notes, right? Does that sound about as far as y'all got with it? Oh, no, y'all talked about sine and cosine a little bit, right? All right. But what I'm going to do is I'm going to take a little bit more time here to talk about, after we've established the right triangle, some of the properties of the right triangle. And the biggest one is called the Pythagorean theorem. So that'll be our next note. So 7.2.2, the Pythagorean theorem. Now, anytime we see the word theorem in math, it means that somebody had an idea, thought that something might be true, and went ahead and proved that it was. And this is the proof that they were actually, well, this is the conclusion of their proof. So there is some way that you can show this, although I'm not going to show it to you like where it comes from. I'm happy to sit down in my office and show you. But if you have a right triangle, and we call this side A, B, and C, A, B for the legs and C for the hypotenuse, there is a relationship between those three sides. And the relationship is that A squared plus B squared must be equal to C squared. And that is the Pythagorean theorem. That is one of the most important identities or equations in mathematics. We will use that later on today for something else. Y'all seen that before? Heard that before, right? So for any right triangle, this is true. Now, if it's not a right triangle, it's not true. And so if this angle right here changes and you no longer have 90 degrees, the question would be, is there a relationship between all the sides still? Do you think we have, like if we change that, make it maybe an obtuse, do you think that we'd still have, not that equation, but do you think we would have one? What do you think? Yes, no? We actually do. It's called the law of cosines. And we're not there yet, because we haven't even talked about cosine yet. But towards later on, we will be able to look at a triangle, and we won't need this angle to be 90, and we will still be able to find a relationship between all the sides. Okay, so, but right now, to start, this is the one we're going to work with. Now I'd like to take, well, before I give you an example, the major result here, okay, the major result of this theorem is this. Given two sides of a right triangle, what do you think? If I give you a right triangle, I give you two sides, not all three, just two. What do you think you'll be able to do? You'll always be able to find the third side. That's the main thing from this theorem, is that if you have any two sides, it doesn't matter which ones you have, just two, you can get the third. So given two sides of a right triangle, you can always find the third. Now that might seem trivial, but I want to practice that. Because even in my Calculus 2 class the other day, when we were doing a problem, we needed to solve a right triangle. There were some people who were getting hung up on it. So it's just one of those skills that we need to practice a little bit here. So let's go ahead and do it. This will be our first example. So the way I do examples is I'll just do example 1. So I'll just say example 1, I underline it. All right, so I'm going to say solve for C. So here's the picture that I'm going to give you. It's a right triangle. We have this side is 5 and this side is 3. And then C is here. So I have two legs, right? I have both the legs, and I'm trying to find the hypotenuse. I'm out of room, so I need to go to the next page. Okay. So the Pythagorean theorem, a squared plus b squared equals c squared. It's very important that we understand that the part that has the two things added together are the legs, right? So when you square the legs and add them together, you should get the hypotenuse squared. So in this case, I'm going to take what? Should I label these? Do you want me to label them? Or, I mean, I could call this one what, A? I could call this one B if I wanted to. Could I call this one A up here and this one B? Yeah, it wouldn't matter. So let's go ahead and just plug this in, right? So what's A squared would be 5 squared plus B, which would be 3 squared, must equal C squared. You square 5, you get 25. You square 3, you get 9. That's C squared. And then you add 25 and 9 together, get what? 34 equals C squared. So now we need to know what C is, right? Not C squared, but C. So what do we do here? We take the square root on both sides of the equation, right? So you walk in here, you take the square root. You walk over here, you take the square root. Some subtleties here. When you are working with an equation, remember, I'm trying to think of you as a person who might need to take more math, all right? So this is I'm trying to look at a big picture here. If you're ever working with an equation and you come in and you take the square root on both sides of an equation, you actually walk in and do that. You must look at both the positive and negative scenario, okay? You always have to do that anytime you initiate the square root, which I did, right? I initiated that process. So I'm going to have to look at the positive and negative answer here. Now on the right side, the square root of C squared is just C. Y'all comfortable with that? Now, that's what happens algebraically. If I have this equation and I want to find C, I come up with these two answers. But within the framework of the problem, C represents the length of a side of a triangle, doesn't it? So since it's the length of a side of a triangle, it cannot be negative. So I can throw out the negative, but I don't want to do that just because, you know what I'm saying? I didn't want to give you just the positive answer because you need to be aware that algebraically there's two possible answers. It's the geometry of the problem that makes you throw one out. Okay, so now I'm going to come up here and say C must be equal to the square root of 34. And I'll put next to it, since C has to be a positive number. All right, now the question becomes, are we satisfied with that answer? Do we want to box that up and move on to the next problem? Well, it depends on what you're being asked for, all right? In this particular case, can you simplify the square root of 34? In other words, can you break down the 34 inside and try and get a perfect square to come out? So does 34 break down? I'll do it on the side here. 34, remember the good old factor tree thing? 34, what multiplies, what is it? 17 and 2. Both of those are prime numbers. Can't break down 17 any further. 2 is broken down. So you can, even if you split it into 2, you can't find a perfect square in there to come out, right? So we're done. So this right here would be what we call, I'm not sure if Christy talked about the difference between exact answers and approximate answers. Does that sound familiar or no? That is the exact answer. The square root of 34. That's the exact value of C. Now, would you like me to tell you approximately what that is? I'll break my calculator out. So go ahead. Someone can break out their calculator. I don't know. Mine's buried somewhere here. Someone here has to have a calculator. Square root of 34. Go ahead. Don't be shy. 5.83? 5.83. Does it go further than that? Oh, nice. So see, it depends on how far we want to go, right? That's why it's called the approximate answer. It all depends on how far you go with the decimal. So when we write 5.83, the standard mathematical notation is to not put an equal sign, because it is not equal to 5.83. It's approximately 5.83. So anyone know what I do there instead? Squiggly equal, right? It's like it really is kind of like it's about, like, you just imagine you're kind of like squiggling. It's approximately, that's what it is. The equal is just kind of like, we're close enough, all right? And that is a mathematical symbol. It's not something that we just use because it's fun. All math people use that symbol. So that answer is the approximate. So on most exams in this class, you'll be asked to give the exact answer, which would be the square root of 34. But later on, we're actually going to be solving triangles and figuring out like the distance between here and some satellite or something like that. And we want to be able to approximate that and get a number that kind of makes sense to us. So in this case, like square root 34, a lot of people don't realize like what that is. You say 5.38, that makes more sense, right? So it all depends on the context of the problem. Any questions? Y'all okay? Y'all seem just all right. All right, let's try something else. In that problem, we were given 2 of the legs, right? And that one most people don't have problems with. It's the scenario where they're given 1 leg and the hypotenuse. And that's the one that people sometimes get mixed up on. So example 2, if we're given, let's say, the triangle (9 and 6). And I ask you to find all the sides of the triangle. All right? So find all the sides. Well, you might want to come in here and label them, right? So I'll call this one A. This one over here, I'll call that 6 is B, and then the 9 is C. And so the Pythagorean identity or Pythagorean theorem says A squared plus B squared must be C squared. And for me, let's see, A is A, so I can't do anything there. B was 6. and then C was 9. So on the left side, we have A squared plus 36 equals 81. We all good with that? And now what? We're trying to solve for A squared, right? Subtract the 36 on both sides of the equation so you can isolate the A squared. So when I subtract 36, you'll be left with A squared equals 45. Now you come in, you initiate the square root on both sides. So A must be plus or minus the square root of 45. However, again, because A is a positive number, right? It's the leg of a triangle. I know from that that A must be equal to the square root of 45, since A must be positive. Can you simplify that and still keep it exact? Yes, because 45 underneath there is what, 9 times 5? So you could rewrite that as square root 9 times 5. Square root of 9 is 3 root 5. That would be the exact answer right there. I'm not a huge fan of going from here to here because it's not really necessary. These are the same answers, all right? But in the book, in this book, you need to have that skill because later we're going to be simplifying things and canceling things, and a lot of times that simplification is coming from doing this first. So we want to be comfortable with it. And then the approximate answer, if you were asked for it, would be, anyone got that yet? 6.708. Now, does it seem right? I mean, look back up here. Like, what if your answer would have been like 11.2? Well, what do we know about the hypotenuse of a triangle? It's the longest side, right? So you can always kind of look back up and say, okay, look, I mean, definitely this number right here, whatever we get has to be smaller than 9. So if I see something bigger than 9, red flag's going to go up, right? All right. Are there any other scenarios that we could have with the right triangle where I give you 2 sides? Is there any other combination? I did one where you had both legs and you found the hypotenuse. I gave you one where you gave you the hypotenuse and a leg. You found the other leg. Is there any other scenario I could give you? That's it, right? I mean, that's the only thing that's possible. 2 legs, give me hypotenuse. Hypotenuse and leg, you give me other leg. There's no other way around it. So if you can do those, we should be okay. I didn't plan on doing this one, but let's do it just anyway, now that I'm thinking about it. Let's do it, the last example. What if we have, I'll work a little faster through this one. 9 root 5, 2 root 3, and 3. Oh, sorry, not 3. Can't give you that side. What about that? I ask you to solve all the sides of that right triangle. So all I've done is I've just put some things in there that aren't that pretty to look at, right? And I'm asking for you to solve all the sides. But it's the same process, right? So I'll label this side A, this side B, this side C. And why don't you try it? See if you can get it. See if you can find out what A is. I'm curious to see what you're going to do when you square B and when you square C. Did y'all work a lot in groups at all, or yes? Yeah? Was it like throughout the class you would do a problem, or was it like at the end just kind of do problems? The end? More at the end? Okay. I try and mix it up a little bit, but we don't have a whole lot of time for group work in a class like this. If you get an answer, let me know, and I'm gonna see if we can get several people with the same answer. And leave your answer as an exact answer. You have something? Let's see here. Okay. All right, hang tight. I'm not saying if that's good or bad, just hang tight. Anyone else think they have it? Anyone need help? So, okay, so you brought that in first and then squared it. So this is it right here. So you brought that in there. 45 and 5, or 81 and 5 here. And then brought that one over. Okay. All right, that looks okay. That looks okay. I can see where people are getting hung up. So let me see if I can help out. Okay. First thing, a squared plus b squared must be c squared, right? We know that. I know a is what I'm trying to find, so there's a squared plus. Now b is 2 root 3, and I need to square that. And then c is 9 root 5, and I need to square that. Are we all okay with this? Just the way I wrote it? That's all right? Now, let's remember that when you take two things, x times y, and you raise them to a power, right? Two things that are being multiplied, and you raise them to a power, that power gets applied to each one of them. So that x times y to the n becomes x to the n times y to the n. This is a property of exponents. So when I'm right here and I have 2 times root 3 squared, that means I have to square the 2 and I have to square the root 3, both of them, right? So it becomes a squared plus, now square the 2, what do you get? 4 times square the square root of 3. 3, right? When you square root, it goes away. So that's this right here. Now equals what? You have to square the 9 and then square the square root of 5. So when you square 9, what do you get? 81 times, when you square the square root of 5, you get 5. Does that make sense? Okay. Now, 4 times 3 is 12. Well, not plus 12. 81 times 5 is 405. All right, this looks a little more manageable, right? Move the 12 over by subtracting it on both sides. If I subtract 12 from 405, I get what? 393. And then finally, square root both sides, right? So I will take square root on both sides. It'll be square root of 393 since a must be greater than 0. So I'm throwing out the negative, but I'm making a little note of it. I don't need that necessarily from you, but I want to be as precise as possible. Okay, we good? Now, does the square root of 393 break down? Shoot, I don't know. Maybe. How would you do it? Like factor tree and try and figure out what number goes in here for sure? 3, right? Goes in there what? 131 times, and then you try and break down 131, and I don't think it does, but we'd be done, okay? This would be fine for me. So you see that when the numbers get a little more complicated, right? Things can get a little more complicated for you. How would you deal with, how do you feel like you would deal with a triangle that had radicals in here like this and fractions? Do you think that would be trouble? Should we try one like that? Because that's really where we're headed. I mean, all of our triangles are going to have radicals and fractions in them. So shall we try one like that? Show you one? Okay. Okay, let me try this one. Let me draw my triangle a different way. Because we get so used to seeing it the same way, it's good to mix it up a little bit. How about root, hold on. How about root 3 over 5 here, and then 4 root 7 over 3 here. Is it safe to say that the idea of using the equation is pretty, I mean, as far as the equation, how you move things around and stuff, that's pretty much okay? It's just when things start looking like this, it becomes more complicated, right? Is that safe to say? Okay, so let's label some sides here. Which one of these are legs? Which one's hypotenuse? What do we have here? What's the root 3 over 5? A leg or a hypotenuse? Leg, right? So call it A. We haven't solved for B yet, have we? Let's do that. What about the 4 root 7 over 3? Hypotenuse, call it C. And then the other one will be the B then. So I know A squared plus B squared must be equal to C squared. A in this case is the square root of 3 over 5. I need to square that. Plus B squared must be equal to the C, which was 4 root 7 over 3. Square that. What do you do when you square a fraction? Square top and bottom, right? You square the numerator and denominator both. So when I square the root 3 over 5, what is it? I'm sorry, when I square the root 3 here, what do I get? 3. And then when I square the 5, what do I get? 25. Yeah? Okay. Plus B squared equals, now over here, be careful. When we're squaring the numerator has 4 times root 7, right? So now, since we're having to square something that's being multiplied, we have to square both the 4 and the root, right? So what happens when I square the 4? 16. What happens when I square the square root of 7? 7 over, what happens when I square 3? Get 9. So we have 3 over 25 plus B squared equals 16 times 7. 112 over 9. Oh, wow. Okay. Now what? You could get common denominator here? Sure. Do you want to move this to the other side first or leave it here? I don't care. We can do it many different ways, but how many of you feel like you would want to move that over first? Yeah? Okay, let's do that. So I'm going to subtract 3 over 25 from both sides. So it disappears on the left side. It reappears on the right side. We comfortable with that? So I really hope that you'll give me some feedback here, because I'm trying to go at a pace right now where I'm trying to feel out where you are, because I have no idea where this class is as far as like just arithmetic. You know, usually after about 6 weeks, I would know this by now, but I don't. So I don't want to come in here and just, you know, blow everyone out of the water. So I'm trying to take this as slow and ask as much as I can. So please respond if it doesn't make sense or something, let me know. That all right? Okay, so now common denominator, you want to do that? All right, it's fine with me. I noticed something right now. I don't know if it's helpful or not. I'm just thinking here. Does 9 go into here? Can I reduce that fraction? I don't think it does, but does 3 go into both of those? No? I'm hoping it does. It doesn't? Oh well. Okay, well, we're going to have an ugly fraction. It's just, that's life sometimes, right? So how do we get a common denominator here? My goodness, that doesn't look fun. You can multiply them together. That's a common denominator, isn't it? So if I multiply those together, what would that give me? What is it? 225? Y'all okay with that? So you could look at it this way. I'm going to bring this up here. I'm trying to keep everything as much on one page as possible. I have b squared. I'm going to basically multiply the first fraction by 25 over 25 on the top and bottom. And then on the other fraction, I'm going to multiply by 9 over 9. This is how we get common denominators, right? We multiply each one by what they're missing. So I multiply the 9 by 25 here. It means I have to do 25 times 112. And then on the other one, 9 times 3. So b squared is 2800 over 225. Oh, I'm move down there. Oops. B squared is 2800 over 225 minus 27 over 225, right? And now 2800 take away 27 is 2773. Over 225. And then you would do what? Square root. So b, and it would be positive, right? Square root of this. And again, I'm just going to leave it like this. I'm not going to try and simplify that, because b is a positive number. Questions? There's obviously a lot more involved with a problem like this than there is with the very first one we did, right? So we just need to be careful with things. Yes? Yes, then you would do it. As the root. Yes. Yeah, that's a good question. Let's say you had come up, let's just say our answer would have been 121 over 7. The square root of 121 is 11. So you could have rewritten this as 11 over root 7. You could have. Does that make sense? Because what we do is we take this and we split it into 2 separate roots, like that. That's a property of radicals, that if you have a fraction in a radical, you can split it into a fraction with 2 radicals. And then you do square root of 121 is 11, and square root of 7 is 7. Now, would that be okay to leave that answer like that? Have you all talked with any of your instructors about leaving radicals in denominators? No? Rationalizing denominators? We'll get to that. Let's not go there right now. I guess I'll leave that. All right. We've used a lot of the class. Wow. Let's now get into what would be considered the new stuff. 7.2.3. The 6 trigonometric functions. These functions are based on an acute angle. Based on an acute angle. The reason why I have to say that is later on, remember I said there's two ways that we could talk about trig functions. One is with the right triangle, and later on it's the circle. When we're dealing with the triangle, your angle in the triangle has to be acute. So this is those trig functions with acute angles. Later on, the angle won't have to be. All right, so if we had our triangle, we label the sides A, B, and C, and put our angle in here, theta. Once I have my angle established, then it's very clear which side is the adjacent side, which side is the opposite side, and then the hypotenuse is always the hypotenuse, right? We define the following 6 trig functions as follows. Sine of theta. That's the way you say this. That's not theta, that's theta. Okay, sine of theta is written this way. Sin theta. And it is equal to, now in math, don't write this down, okay? But in mathematics, you see the two like a colon in front of an equal? That means we are defining something. Like I'm telling you this is what it is. Now I'm not going to put the colon there because the book doesn't put the colon, but it's a way of letting a reader know, look, we are saying that I'm telling you what this means. Here's what it means. But I'll just put equal. Okay? So the definition of this, what this thing right here means is this. It's just the ratio of two sides of the triangle. Ratio meaning a fraction. It's just the B side divided by the C side. So if I'm looking at this angle right here, theta, and someone says, hey, what's sine of that angle? What's sine of theta? You would look at the B side and divide it by the C side, and that's the answer. This is just a fraction. Okay? Now, another way of looking at this, you could say, or if you don't like to look at it in terms of B and C, you could say that that's the opposite side over the hypotenuse, right? So you could say opposite. I'm just going to say op over hype. I did see that in your notes, right? That was in your notes from before. That's sine of theta. Now, after sine of theta, we have the next trig function, which is called cosine of theta. And the way we write that is cos theta. And cosine is your adjacent side, A, divided by your hypotenuse. So instead of, if you're looking at cosine, instead of taking the B and dividing by C, you look at the A and divide by C. So another way we could look at that is it's the adjacent, right, divided by the hypotenuse. You might be saying to yourself, why? Why do you have a triangle? You start defining these functions. Well, it's because there are very, very nice relationships between all these functions and how they behave as the triangle changes. So it becomes extremely useful, as we will see. Spend a lot of the rest of the class doing that. The third of the sixth trig functions is called the tangent of theta. Tangent of theta is written tan theta. It is always your B side over your A side, which in terms of opposite, adjacent, hypotenuse, what is it? It's opposite over adjacent. Opposite over adjacent. Those are the first three. Now, the next three are very much connected to these. So before I get to the next three, I want to show you something that I'm not sure if Christy showed you this or not, or told you this. Did she tell you SOHCAHTOA? Did she mention SOHCAHTOA? Did she tell you the story about SOHCAHTOA? She doesn't like it? Why didn't she like it? Well, as long as I've been teaching, I've heard that from students. It's a thing that sticks, and if it sticks, then I recommend using it. I always tell, there's a story about this Indian girl who was really good at math, and her name was SOHCAHTOA. And so, did she tell you what it was, or just mentioned it? So, it didn't tell you like how you use it. SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Very easy to remember your trig functions that way, in my opinion. Obviously, we don't all have the same opinions. But I've always remembered that. Even to this day, if someone, asks me what tangent is, just for a millisecond, I think TOA. And I have it, I don't, you know what I'm saying? It can become that automatic for you. So do y'all see that if you want sine, it's opposite over hypotenuse, right? S-O-H, so, ka, toa. Yes? Does it need any further explanation? All right. So use it or not. Now, the other three are just the reciprocals. Now, reciprocal, remember with the fraction, if you have a fraction, you can always reciprocate it by flipping it. That's all the next three are, the reciprocals of these. So the first reciprocal is, instead of doing B over C, what if I did C over B? We call that cosecant. Cosecant. So that's my next one. I'll do these in a different color. Cosecant of theta is written CSC theta, and it would be C over what? I said it's the reciprocal of the sine, so it'll be C over B. Or if you wanted, you could say it's the hypotenuse over the opposite. The next one would be the reciprocal of cosine. So instead of A over C, C over A. And we call that one secant. Of theta. Secant theta C over A. Or you would say hypotenuse over adjacent. I can't believe Christy didn't like SOHCAHTOA. All of our conversations about math, I never got that out of her that she didn't like it. Oh well. All right, what would be the last one then? We've done reciprocal of sine, we've done reciprocal of cosine, so we just need the reciprocal of tangent, right? Flip that one over. Instead of b over a over b. That's called cotangent. I didn't name these, okay, so don't get upset with me about the names. Cotangent of theta. Later on, I'm going to show you a really cool picture of how all of these are connected to each other in one picture. And it's really cool. But it uses the circle instead of the triangle to illustrate it, so we're not there. But there is a connection all in one nice graph that you can see how these are all related to each other. All right, so we write this COT, theta, and this one is A over B. Or you would say adjacent over hypotenuse. Now, SOHCAHTOA works for sine, cosine, and tangent. It helps you remember those, right? SOHCAHTOA? But I've never heard anyone have anything for these three. What's that? Oh, yeah, thank you. Thank you. Opposite. Adjacent over opposite. So we could maybe come up with our own word, but we're not going to. So the way that I remember cotangent is I first say, well, cotangent's the reciprocal of tangent. So I go TOA, which is opposite over hypotenuse, or TOA, sorry, opposite over adjacent, and I just flip them, adjacent over opposite. So it's all going to be how your brain wants to work this out, all right? But on your formula sheet, all of these will be provided, okay? Your formula sheet has them, but you should not become dependent on the formula sheet. Like when you move to Calculus 1, because I know a lot of you said you have to take Cal 1. You do not want to be in Cal 1 and the instructor's like, okay, what's sine of something? And you're just like, hold on, and you're breaking out your formula sheet. Because that means you haven't worked with them enough. You know, you haven't used them enough that they've become memory. And that's where we want to go with them. All right. Example 4. That's it. Those are the 6 trig functions. And we might be sitting here and go, okay, so we got these 6 functions, big deal. I mean, like the rest of the class is basically based on all those 6 functions, believe it or not. Everything we do from here on out is all based on those 6. All right, so here's an example. Give you a right triangle. Again, I'm going to change it up a little bit. Let's say that this is 6, this is 10. And let's call this angle here theta. Find all 6 trig functions of theta. That's it. That's a test problem right there, all right? So that means I need to find sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta. I need to find all of those. And every single one of those answers should be a ratio of 2 sides of the triangle, right? So let's start with sine theta. What would sine theta be? Well, I'm going to go off of not the A over B or B over C or C over B. I'm going to go off of the opposite hypotenuse adjacent idea because I think it's easier when we're working with triangles to look at it that way. So sine is what over what? Which one over which one? Opposite over hypotenuse, right? This is opposite over hypotenuse. Now, which side of this triangle is opposite of theta? The one we don't know, right? the one we don't know. But this is a right triangle, and I have given you two sides of the right triangle, haven't I? Which means you have to go find that third side. Once you have the third side, then you can find all the trig functions. Yes? So this is almost like a two-step problem. First step, solve the triangle. Second step, create all your ratios. All right. Now, I know it's our first day, so I'm not going to do this to you, but just to give you an idea of the way that I work, this would be a point in time where I would say, you do this problem on a separate sheet of paper, put your name on it, put today's date, we'll take it as a quiz grade, you can work together. Okay? That's an example of the way I would do a quiz, just on the fly. So I would like for you to do it today. I think it's fair. I think everyone will get to the answer, so we can count it as a quiz grade. Do y'all want to do that? Or do you just don't want a quiz today? We won't. What do y'all want? This okay? Let's try it, okay? If you get stuck and you can't do it, then maybe I'll change my mind. But for now, let's separate sheet of paper so you can turn it in. Work together if you need to, or if you're one of those people who want to work alone, you work alone. And see if you can figure out, remember, all 6 trig functions, all 6. What I'm going to do is, while you're turning them in, do those look like the correct, what you got also? 4/5, 3/5, 4/3, 5/4, 5/3, 3/4. Does that look right? Anyone else? Here we go. Thank you. So a quiz like that is really just designed to because I hadn't even done one like that, you had to somehow take the ideas and put them together and do a problem yourself, right, without being shown how. So a problem, I think that those are somewhat not easy. I don't want to say easy because that's kind of insulting sometimes when people say things are easy. But that's different than a quiz that you would walk into beginning of class where I say, okay, we're going to take a quiz over your homework. That's a different type of quiz. But these types of quizzes help your grade, and it encourages you to be here and pay attention and ask questions. All right, so we're good? Okay. Now, the next thing we're going to discuss, and we still have time, all right. We're at 7.2.5. We have what are called the fundamental identities. You all just let me know if the light needs to be turned back off, if you can't see that well enough. The fundamental identities. So here they are. First one, cosecant theta is 1 over sine theta. Now let's think about why that's true. The way we defined it. All right, so that's the identity. Towards the side here, I'm just going to show why. All right, here's why it is. Well, cosecant theta, oh, you know what, let me start this way. 1 over sine theta is the same as 1 over, what was the sides for sine? Sine was opposite over hypotenuse, right? So this was opposite over hypotenuse. But if you have 1 divided by a fraction, doesn't that just reciprocate the fraction? Yes? It flips it. So you get hypotenuse over opposite, which is, by definition, when I defined cosecant, I said cosecant was hypotenuse over opposite, right? So anytime we see a cosecant theta, anytime we ever see cosecant theta, we can always replace it with 1 over sine theta if we see so fit. If we want to, we can. On the other hand, if we ever see 1 over sine theta, we can always replace it with cosecant theta. Now, the way that this would also work is if I see sine theta, isn't that 1 over cosecant theta? Yes? If cosecant is the reciprocal of sine, then sine should be the reciprocal of cosecant. Now, the ones that I'm going to highlight here are the fundamental identities. I mean, this one is the fundamental identity, but this other one comes, you could also use that. The book doesn't list this one right here as a fundamental identity. It just lists this one. But you should be able to see that this leads to this also. Okay, next fundamental identity is the secant. So what do you think it says for secant theta? It's probably 1 over what? Cosine. It's the reciprocal of cosine. And then we have that cotangent theta is the reciprocal of what? Tangent. Now on those, the ones I just did, I did not explain why, but I hope after showing you this first one over here that you could write those out and show yourself that it is the same thing. Okay, so those are our fundamental identities. These are all three of these right here are called the reciprocal identities. Reciprocal identities. Because it shows you how a trig function is related to its reciprocal of another function. The next two identities that I'm going to give you are called the quotient identities. And they are tangent theta, this is a big one, is sine theta over cosine theta. Why is that true? So let's convince ourselves that this is true. What is sine theta by the definition? And let's use the SOHCAHTOA thing. What's sine? Opposite over hypotenuse. And then divide that by cosine. What's cosine? Adjacent over hypotenuse. And if you have a fraction divided by a fraction, you can flip that second fraction up, right? And so this really becomes opposite over hypotenuse times the reciprocal of the bottom, which is hypotenuse over adjacent. And what happens there? The hypes cancel, right? And all you're left with is opposite over adjacent. But what is opposite over adjacent? It's tangent. You see? This one is going to come into play a lot. Whenever we say, oh, well, what's tangent theta? Sine theta over cosine theta. And then the next one is cotangent theta. What do you think that is? If cotangent is just the reciprocal of tangent, and we just said that tangent was sine over cosine, then cotangent should be cosine over sine. So those are our identities that we're going to have here. Let's do an example now. This is example, what, 5? I lost track because I threw an extra one in there. Is this 6? All right, so for this example, if sine of theta is root 3 over 4 and cosine theta is 1 over 4, find the other trig functions. Of theta. So I want the other ones. How many other ones are there? 4, because I've given you 2, right? I've given you what sine theta is. I've given you what cosine theta is. I want to know what the other 4 are. So I need to know what tangent theta is. I need to know what cosecant theta is. I need to know what secant theta is. And I need to know what cotangent theta is. All of those I'm looking for answers, right? Which of these can I just right off the bat say what the answer is? What's that? Which one? Cosecant, because cosecant is the reciprocal of which one? Cosecant's the reciprocal of sine. That means cosecant should be that sine one flipped over. So what's that sine one flipped over? 4 over root 3. Which other one can I get right off the bat? Secant, because secant is the reciprocal of cosine. So secant should be 4 over 1, which is 4. What else can I get now? Those were just by looking, right? How can I get tangent? How can I? It's sine over cosine, right? That's what we just said, the quotient identity. I'm kind of a little bit out of room, but if I take sine theta, which is root 3 over 4, and I divide it by cosine theta, which is 1 over 4, so do you all see that? Tangent theta is sine theta over cosine theta. And then flip that second fraction up, root 3 over 4 times 4 over 1. The 4's cancel. I'm left with square root of 3. I'll see how that worked. And then, what's cotangent? There's a couple of ways I could look at it. I could say cosine over sine, right? Or I could say it's the reciprocal of tangent. And I already know what tangent is. What's the reciprocal of tangent? If this is really like a root 3 over 1, isn't it? So if I flip that, it's 1 over root 3. That's it. I have my 4 answers. Now, normally the book will not like to leave answers with radicals in the bottom. It's called rationalizing a denominator. So let me take a minute to talk about that, all right? Let's keep these 4 answers in mind here. I'm kind of going off what I planned on talking about. What am I at? 7.2 point, I'm going to say 6. Rationalizing denominators. Okay, if we have the answer like we just had, it was, do we have 4 over root 3? Okay, for one of our answers was 4 over root 3. The book is always going to want you to get rid of the root in the bottom. They don't like square roots in the denominators. So they say, what you do, anyone know what you do? Multiply the top and bottom by root 3. That's what we call rationalizing the denominator. Now the reason why we do this is because when you do the bottom now, root 3 times root 3 is root 3 squared, right? On the top is just 4 root 3. But root 3 times root 3 being root 3 squared, the root goes away, doesn't it? And you get 3. So your answer would be 4 root 3 over 3. Now keep in mind I'm saying that these two are equal, okay? Your original problem was 4 over root 3, right? We changed it by multiplying it by, what number is this right here? 1. When you multiply something by 1, it doesn't change the problem, right? It doesn't change it. So I multiply by 1, I get something that looks different. But they're the same answer. How many of you were told, like, you always have to do that? Okay. I was told the same thing. I was told you always have to rationalize the denominator, and it always bugged me because it's like, well, why? Like, this is the same answer. Like, why do I have? Why don't you like square roots in the bottom? Why is it such a problem, right? Calculator doesn't care, does it? Calculator doesn't care if you type in 4 over root 3 on your calculator and get the same exact answer as you get if you type in 4 root 3 over 3. So what's the story? Well, I actually looked into it, and I found out, and it's actually pretty interesting, all right? Before calculators, okay, before handheld calculators, math people would have to do computations like this. And so there were certain numbers that they would run into all the time. They would see like square root of 2, square root of 3, square root of 5. They would see like pi. You know, these are numbers that come up in math a lot. So since they didn't have calculators, they just had to memorize what these were, approximately what they were. So like people back, 50 years ago knew that pi was like 3.1415. And back then, before calculators, it was almost like the level of your math dorkiness was measured by how far you could go out with pi. One of my colleagues who's in his 60s at one point knew pi out 120 digits, still knows it 60 digits out. And so it was like, that was the cool thing. Like back then, if you were a math dork, it was like, I know pi to 120. What do you know it to? 80, and they feel all like nothing. So I think the world record is 60,000 or 16,000. I can't remember. There's a guy who knows pi that far. Interesting. If you look it up, we won't talk about it. It's pretty cool though. I mean, I don't think it's cool that he knows that. It's the way his brain works. He talks about that, and it's very cool. Yeah, he sees pictures. So it's more like if you were to try and describe to me what it's like to get up in the morning and come here. Like you could say, I'll get up, and when I step out of bed, I have like my dressers here, and then I walk in, I've got like a white towel on the door. Like you could, in a lot of detail, describe your, the picture of your life. And that's the way he sees numbers. So it's just like walking through a scenery. It's weird. Okay, but so all these numbers, these people back then used to know these. This was like 1.414, and then so on and so forth, right? So they would get working on a problem. They would be in a calculus class or pre-calc class, and let's say that they ran into something like this one right here, and they were working on a problem. They got 1 divided by the square root of 2. Okay, let's say they ran into that, and they need to figure out what that was. They didn't have a calculator, they didn't have anything they could go to, but they needed an approximate answer. Well, if you go back to old school division, and I mean old school division, you take the thing on the top, 1, and you divide it by what's underneath, right? So you divide it by 1.414. Well, if I try this is a freaking disaster, okay? How many times does 1.414 go into 1? Well, it doesn't. So I'd have to put a decimal, add a 0, bring a decimal up here. Now I would say, like, how many times does 1.414 go into, like, 10? I don't know. How many? I don't know. Take a guess. I don't know. You would have to kind of guess at it, right? And then maybe it's 6 or 7 or something like that, somewhere around there. You'd have to actually multiply 1.414 times that and figure out what it is and hope that it would be enough. Does that make sense? It would be a mess. However, if you take this 1 over root 2 and you rationalize it, root 2 on top, root 2 on bottom, then on the top you have root 2, and on the bottom now you have what? 2. Now that's the same exact number, it just looks different, doesn't it? And when I do my division, this time the part that goes on the inside is the root 2. So that's the 1.414, right, that the person has memorized. And on the outside is what? 2. Now, 2 does not go into 1, okay? So does 2 go into 14? 7 times. 7, 14, you come down here, you get 0, you're left with 14. 2 doesn't go into 14, so I put a 0. 2 goes into, 2 doesn't go into 1. 2 goes into 14 7 times, so I get 0.707. You see how much easier that is to do by hand? That's the reason. That's the reason. But it's obsolete now, right? We don't need that. But it's good to know, I think. It's kind of it kind of upset me when I learned about that. And I was like, all this time I've been told I have to rationalize denominators, but I've never really been told why. No one's ever given me a good explanation. This makes sense. Just don't really need it. For us, everything in our book is going to be rationalized. They're going to rationalize every answer. So I'm going to continue to do it, but I just want you to know there's a little asterisk there. I don't like it, but we do it because that's the way it's always been done. Okay, well, let's see. We still have a little bit of time. My goodness. Yeah, I can show you the last thing, and then we'll call it a day. I think we've done good. Moved a little slow, but that's all right. 7.2 point. Where am I? Am I at 6? 7. See, I threw myself off by throwing more in there. All right, the Pythagorean identity. Now, earlier today, we said that if you have a right triangle, A, B, C, right? And let's even throw a theta in there, like that. The Pythagorean identity said A squared plus B squared was C squared. We all took that on faith as being true, right? We were all okay with that. What I'd like to do right now, I would like to divide everything, both sides of the equation, by C squared. Is that okay with you? Now, you can always divide both sides of an equation by anything except 0. And in this problem, C is obviously not 0 because it's the hypotenuse of this triangle. So come in here, divide everything by C squared. Everything by C squared. Everything by C squared. Now on this first fraction, do you agree that that's the same as A over C squared? And then on this next one, that's the same as B over C squared. And on the last one, or on the other side, what's the other side? C squared over C squared is 1, isn't it? Y'all follow this though? A squared over C squared, you put it in a fraction, when you square it, the squared would have gone to both of them. So I'm almost like pulling the square out and making a fraction. In this triangle, what is the ratio A over C? What trig function is that? A over C. Adjacent over hypotenuse. Cosine theta, right? In this picture, isn't that cosine theta? So that's cosine theta squared plus, what's B over C in our trig functions? That's opposite over hypotenuse, which is sine. Are you all still with me or not? And then equals 1. So this means cosine of theta, then you square it, sine theta, then you square it, right? One more thing and we're there. This is purely notation. Notation, when I say this is just notation, I mean, we just agree as math people, this is the way we're going to write this, all right? Instead of writing cosine theta with a set of parentheses and squaring it, which makes a lot of sense, right? We're going to square that thing when we're done with it. Instead, we write it this way. We put the square right here and we get rid of the parentheses. It's one of the few times in math we do something like that. but that's the way we write it. This right here means that. This means you square the cosine. If I use that same notation, this one here turns into sine with the little superscript, sorry. And this, everyone, is our Pythagorean identity. There are 3 Pythagorean identities. This is the most important one. You should have this memorized. Every student coming out of pre-cal, going into cal 1, should know sine squared theta plus cosine squared theta equals 1. It is a fundamental identity. Got it? I'll show you something real quick. Let's see how quickly I can pull this up. I may not be able to find it that fast. I'm trying to find in my this is my Cal 3 class. I was going to try and find a problem that I used that identity in, where we turn something into 1. I'll show it to you later. But, I mean, it's just used so often, things turn to 1, we're done. We will pick up here. We have a lot more to talk about. Let me turn off my recording and ask you a question. Where were we here? I had a homework assignment. I think I had. Did I not write it down? Darn it. How about I email you the homework? Is that fair with everyone for now? Because I just didn't know how far we would get today with this. I didn't get quite as far as I wanted to. So I'll just email you the homework.